right type of microns, like 0.02 microns, that's probably the spot as far as you're going.
Okay, guys, so gals, we have covered fluid statics, we've covered fluid dynamics, by looking at Bernoulli's equation. We talked a little bit about phases of gas and liquid. Now I want to get a little bit into heat transfer technologies, and I'm really hoping that John has a few home tours lined up for you in this course. There are a few homes in Missoula that are extremely energy efficient, and I think really the big point of this course is how do we continue to live as comfortable, civilized human beings on planet Earth without using either an excessive amount of energy or an excessive amount of money, right? So, let's design a system up front. Maybe it costs a little bit more, but if it saves you energy and therefore money down the road, then you've got a high-value home. On that note, I just want to take one quick little sidestep, and I think a lot of my energy tech students have seen this, but this is, in my mind, the big picture on energy sustainability. This is something that will affect all of us, maybe more than we are willing to admit right now. But let me just show you this one figure that I dug up not too long ago. The paper was just published last year, so it's relatively hot off the press. And it's Shramsky. So this came out of the Proceedings of the National Academy of Sciences. And what these guys are doing is just taking a look. So I talked, last lecture, each home uses about a kilowatt of electricity, and you can multiply that by 5 in terms of heat. Well, where does that energy come from? Well, it comes from nature, and there's a lot of different ways to extract energy from nature. But what we are doing as a human civilization is typically taking the chemical energy that the Earth has been storing for however many million years and using it, right? We're burning coal, burning oil, burning fossil fuels, exhausting unrenewable nuclear fuels as well. This is how much biomass there is. If you want, I gave a whole lecture on that, so I'm not going to dig too deeply in it. But this is just like our gas tank for the planet. And down here is a graph of how quickly we're using it, and this is just phytomass, and that's gas, oil, coal, you name it. It's not the happiest curve. The good news is it's starting to slow a little bit. And so right here, there's your argument for renewable fuels, because that stuff is not coming back. This is the one I wanted to show you, though. So the the blue line is how many people live on planet Earth, and so you can go back. Only 400 years ago, when there were well under 1 billion people. You can come up to now where we're knocking on, I think, in fact, there are more than 7 billion people on the planet right now. This is how much energy our civilization uses. This is how much it used. You can see that there's a few flat spots here. One of my favorites, though, is this one, in terms of how much energy is how many years worth of energy are left. At our current rate of consumption, we've got 1,000 years of energy left. This was the plague. So when the plague hit it was almost like, okay, the engine went on idle. The Earth's techno engine went on idle, and we weren't There was even a little bit of a rebound there as forests regrew. So those are the two curves. One is how many people are on the planet. This is how much energy we use. This is the energy per capita. That's how much energy each man, woman, and child, on average, uses. So remember that kilowatt I said before, and then you multiply that by 5. Let's just make it easy and say that an average household has 4 people living in it, and it's running at 4 kilowatts. Well, then you count your car uses some energy. This building's using some energy. So right here, as it turns out, and this is about right. As it turns out, we're all at about 2 kilowatts per person. So just to sustain our current comfort level, it takes 20 human powers. I know you took 101 and 102, you're well aware of this, but it takes about 20 human powers to sustain one person. The interesting curve here for me, though, is that this thing actually turned sharply down for the first time kind of ever a few years ago. Now, that's one of two things. Either people's quality of life is going down, and I'm sure that's true for a lot of people. You look at Somalia, you look at a lot of these refugees around the planet, like, oh man, that's a turn for the worse. Like there's no food, there's no fuel, the resources aren't there. It could also be, the brighter side, and that's, I think, the point of this class, is that we're becoming more efficient. So you can look at fuel efficiency standards, you can look at hybrid cars, you can look at some of the buildings that hopefully we'll see, and say, you know what, it really does not take that much energy per person to make us live comfortably. So that's the curve I wanted to show you kind of going into this next example. You'll see it, Rain. Okay, now, one of the homes that I'm hoping we can see, this, one of the homes I was hoping we could see this, this semester is Tom Javins. Tom Javins used to be the facilities manager at the university. He redid his he actually built a new home. He is able to run his whole HVAC system on about 52 watts. So he's got basically the equivalent of like 4 or 5 computer fans running his whole house. Now, what he did though, I've seen the house. What he did to do this, he's got giant ductwork, like 12-inch tubes running through his house. Typically, you look at you look at the ducting in a lot of houses, maybe 6, maybe 4-inch tubes. The deal is, and as expected, in a 12-inch tube, the delta P, the change in pressure, is small. If you've got a bunch of little skinny 4-inch tubes, I think you guys were talking about forcing fluid through nanotubes or something. The smaller the tube, the more pressure it takes to shove the fluid through there. I'm not going to dig into the mathematics, but a 4-inch tube, the delta P is large. So one way that Tom Javins was able to let his whole house run on 52 watts, pumping heat around, was he's just used larger tubing is one. Okay. Another one, and since we're sitting here right now, I'm going to jump just a little bit ahead and give you one more problem to think about, because I do want to look at this 4th topic, heat transfer technologies. So let's hop back to Shramsky just for a second. Let's look at this energy per capita in kilowatts, and here's the problem I'm going to give you to figure out. So let's say you're going to build your own home, and you're going to do Tom Javins one better, and you're actually going to get all of your energy from renewables, and you're going to actually, I think he's got gas. But what I want you to do is this. The problem I want you to figure out is, well, there's two problems. Here's the first one. How much energy per person per year? Because what we're going to try to do is actually devise a thermal fluid system for a house where you can store all of your thermal energy for a year. We'll figure that out just with some simple mathematics. So first, take a look at this. Take a look at this.
You said one person?
One person. I want to know how much energy one person requires.
Kilowatt times 306?
Yeah. Just use this. Yeah. Use the same math that we used last week, and just tell me how much. You can do it in kilowatt hours. You can do it in megajoules. You can do it in BTUs, calories. I don't care. Just tell me how much energy per year, and then what we're going to do is design a seasonal thermal system for a house that stores all your thermal energy for you. We'll just see how big that has to be. So we'll do a little building energy engineering. So I will pause this while you tell me how much energy per person per year, and we'll come back.